So today we're going to be looking at Spearman's rank correlation coefficient. So we've already looked at Pearson's moment correlation coefficient. Why would we need a different correlation coefficient? With the PMCC, we actually had an underlying assumption about the two different data sets. We'd assumed that both of those samples were drawn from populations that had a normal distribution. A normal distribution is a symmetrical distribution where the majority of results are in the middle and there are fewer and fewer results as we go off towards the extremes. So this is something like the height of people in a specific country. So the majority of people are average height, with very few people that are extremely tall and very few people that are extremely short. We will definitely look into the normal distribution in more detail later on, but for now I just want to point out that there was an underlying assumption that we made when using or calculating the PMCC. Unless we know our data has come from two populations which are normally distributed, we shouldn't be using the PMCC. We have to use an alternate measure for correlation. Additionally, we saw that the PMCC is what we use when we have a linear relationship or a linear association between the two different data sets. If we're not looking for linear correlation, then we have to once again use an alternate correlation coefficient. And that's what we'll look at today, Spearman's rank correlation coefficient. So, Spearman's rank, we'll use similar notation. RS is popularly used to make the difference between PMCC and Spearman's rank. It really is just a special case of the PMCC for the conditions that are mentioned. And instead of using the raw data, we use the ranks. We're using the first place, second place, third place as the data. So in most cases, we're going to rank in order of highest to lowest, with the largest X value being given the rank of 1, the second largest X value, the rank of 2, etc. And then we do the same thing to the Y values. Rank. The choice of using Spearman's rank correlation coefficient, you will usually be told to apply Spearman's rank, but here's the reasons when we would. If one or both of those data sets are not from a normally distributed population. 2, if there's a non-linear relationship between the two data sets. And 3, because one or both of the data sets have already been ranked, meaning we've lost the original data for one of those sets. We know the order, but we don't know the original data. Okay, let's actually have a look at what happens under Spearman's rank. So, in this situation, here are the ranks for these students' math scores, and here are the ranks for their English scores. The best performing student in maths isn't necessarily the best performing student in English, but can we measure whether there is still a relationship between them? Okay, so if we were to calculate the PMCC of those ranks, so the numbers in orange, if we were just to carry out our PMCC calculation on them, we would get negative 0.4. Let's have a look at what the value of the Spearman's rank correlation coefficient is telling us. So let's look on the left. If the best student in one subject was also the best in another, and second place in one subject was second place in another, third place matched with third place, and fourth place matched with fourth place, we would have a correlation coefficient of 1. They're in perfect agreement. First place here was first place there. Last place here was last place there. Looking in the middle, first place in one sport was last place in another. Second place matched with third place matched with second, and last place matched with first. These almost seem to be opposites. So the correlation coefficient, the Spearman's rank correlation coefficient in this case, would end up being negative 1. These are ranked in reverse order. And if we had a little mix of both, where there wasn't a clear indication of which way the ranks were going to match up, we may well get a correlation coefficient of 0 or somewhere in between. So we're going to interpret Spearman's correlation coefficient in very much the same way we would interpret Pearson's correlation coefficient. Smallest possible value we should get is negative 1, and the maximum possible value we should get is positive 1. we don't actually want to be calculating Spearman's rank using the PMCC technique. There is a much easier technique that's been developed and there's a formula that's been deduced, but this is how we're going to need to find it. For each of the ranks, or each of the pairs of ranks, we're going to need to find the difference between them. So, if we list them out next to each other, we just need to calculate the difference between each of these ranks. So, -1, 0, -2, and +3. With these differences, we're going to square them to eliminate negatives, and then we're going to want to sum them together. Here's the formula that we're going to use. The Spearman's rank correlation coefficient is going to be 1 minus 6 times the sum of the differences squared, all over n times n squared minus 1. So let's start by squaring those differences and adding them together. And because we know we're going to square them, we can almost ignore the negative that's already there. So I really want 1 squared, 0 squared, 2 squared, and 3 squared. When we add those together, we get 14. So substituting this into the formula, we should get 1 minus 6 times 14 over 4 multiplied by 4 squared minus 1. When we do that, that's a much quicker way of us getting our negative 0.4. Okay, so let's actually just look at that on a larger scale, just so you can see it in action. And I'm going to compare it to the PMCC calculation that we could have done. So this time round, 2 tea testers were asked to rank 9 different blends of tea in order of their preference. And here we have the different blends, lettered A to I, and we have the ranks that the 2 testers gave them. On the left hand side in the table, what I've done already is I've taken the original ranks and I'm treating them exactly like we would for the PMCC. I've squared each of the x values so I can find the sum of x squared, squared each of the y values so I can find the sum of y squared, and then I've done the co-product, and then I've done the product, and then I've calculated the product of the x and y's, and I've summed those together as well. So I've got 285, 285, and 258. For each of those, they've contributed to calculating S of xy, S of xx, and S of yy, which I've put into the formula for the PMCC correlation coefficient. Substituting all of those in, we get this mega calculation down at the bottom in all of its glory. It leads to 0.55. How about if we use the shortcut formula? With the shortcut, I once again have the ranked data for taster 1 and taster 2. But instead of squaring and finding the products and the sums, I'm just looking for the differences. And actually, I prefer to think of the modulus of the difference. So the modulus of the difference already ignores any negatives. So just the magnitude of the difference between each of these. I'm going to square each of those differences. And then I'm going to sum them together and substitute straight into that formula. I know from the question that n equals 9, so I'm going to be able to write out this formula. Well, the sum of all of these values is 54. I'm going to be able to write out the formula as 1 minus 6 times 54 over 9 times 9 squared minus 1. Very easy calculation to do on a calculator. And look, we get exactly the same answer, 0.55. This technique on the right hand side is what we should be using for Spearman's rank correlation coefficient calculations. Let's move on to a stipulation here. If you notice, this formula is always predicated by the fact that if there are no tied ranks, then we can go ahead and use this formula. If we do have tied ranks, it causes this shortcut formula that we're using to become less accurate. Well, less accurate compared to the long way round. If we have tied ranks, we should be using the PMCC formula with the ranked values. Okay, but what exactly are tied ranks? Let's have a look at this data. Anytime in the original data we have 2 values that are the same, it wouldn't actually be correct to give them different rankings. So looking here, we have some data that's already been arranged in order. I have the number 350 twice. It wouldn't be right to give one of those observations a rank of 2 and the other one a rank of 3. What we do instead is we take the average of the ranks that we would have assigned, and we assign them both their average. So 3 and 2 would average 2.5. We give both of these data points the rank 2.5. Okay, let's have a look through the data. Are there any more duplicates? 800 appears 3 times. The ranks are 6, 7, and 8. We need to calculate the average, the mean of 6, 7, and 8. We can add them together and divide by 3, but hopefully you can spot that it's going to be 7 as the average. Each of these are going to be given the rank of 7. Now, as we look across the ranks, averaging these have not interfered with any of the others. So I've got 1, 2.5, and 2.5. But they should have occupied the place of 2 and 3. I then need to start the rank count from 4. Okay, don't make the mistake some students make of just looking for the next integer value and the next rank assigning it 3. Overall, even with these modified ranks, they should still have the same sum as before we assigned the 2.5 and the 7s. Okay, so let's just have a look at this question. So the marks of 8 pupils in French and German tests are shown below. And as we can see, there are some students who have achieved the same score. Okay, we'll just look at part A of this question. This question actually instructs us to use the Spearman's Rank shortcut formula. So we're going to go ahead and do that. If it didn't, we would need to revert to using the PMCC because of the tied ranks. Okay, so I'm just going to pull that data into the table so it's usable. Okay, as I scan through, I can see that 2 students have scored 55 for French. So, ranking the data. These would have been 6 and 7. Average of 6 and 7 is 6.5. That's what I've used for the rank. When it comes to the German score, once again we have duplicates. There are 2 students who scored 40. So once again, the ranking, we need to take care of using the average rank. The average of 3 and 4 being 3.5. From here, we'll carry on as usual. We would find the modulus of the differences. We're going to square these and sum them together. Okay, so now that we've got that 69.5, we're just going to substitute into the formula. N was given to us in the question. We know that N equals 8. And we're just going to substitute in 1 minus 6 times 69.5 over 8 multiplied by 8 squared minus 1. Okay, putting all of that in gets us a correlation coefficient of 0.17. There's very weak positive correlation between the score you get in French and the score you get in German. The question goes on to ask, without recalculating any correlation coefficient, what would happen to our answer in part A if we change pupil H's mark for German to 38%? Pupil H had scored 34. If they score 38, so their score has changed, but their rank hasn't changed at all. They're exactly the same rank as they used to be, so this isn't going to change any of the calculations that we've done. What would happen if a 9th student was added who had scored very high in French and very high in German? In fact, the best score in French and the best score in German. Well, that would change our correlation coefficient, and that would actually make it stronger, because there we have somebody whose scores agree, where the ranking that they have for each of those 2 scores agree with each other. Part C goes on to tell us that the teacher collects additional data from other students in the class and finds out that there's now lots of tied ranks. There's lots of students who have achieved the same score within the test. How would this teacher now go about measuring the correlation? And this is where the PMCC technique is going to kick in. So we're going to need to use the tied ranks, or we're going to need to use the rankings that we have for the entire class. But instead of using the shortcut formula of the differences and squaring the differences, we have to revert back to calculating it with the PMCC. So we'd apply tied ranks to each of the students as necessary, and then we would calculate the PMCC from the tied data, rather than using Spearman's rank correlation coefficient formula. Okay, so here are situations and stipulations around Spearman's rank.